This lesson is from 2021-2022, and it is the second day of 12-2. These are the worksheets from class. We will not be going through all of these problems, just going to do a sampling of some variations from yesterday's lesson. The first one we're going to start off with is the very back page here. It says you are given the cost to build a square deck for your house, and it gives us this table of values, and it says use re-expressed data to create a model that predicts the cost of the deck based on the width. So I already have the data in the calculator. Let me clear that list out. In L1, L2. Now it didn't specify in the original instructions, I wrote this in, of what transformation to use. Yesterday's transformations that we focused on were taking the natural log of x, taking the natural log of y, or taking the natural log of both. Those are very common transformations, and playing the probability game, if you were to see one on the AP exam, it would probably be one of those three from yesterday. But transformations are not limited to just those. So this is an example where the transformation is going to be working off of the square root of y. All right, first thing, let's get a look at what the data appears to be as is. So I'm going to set up a scatter plot of L1 versus L2. Make sure I don't have anything, clear this stuff out. And I'm just going to zoom 9 it. And the pattern, or the form, certainly appears to be curved. It does not appear to be linear. So what I'm going to do is go to Stat, Edit. I'm going to follow their instructions, and we're going to use the square root of y. Well, the y's are in L2. I'm going to hit square root L2, enter. And now the original x's, untransformed, are in L1. And the square root of y's are in L2. Let's take a look to see if that appears to linearize the data. So now I'm going to look at L1 versus L3. I'm just going to zoom 9 it. And that certainly appears to be more linear than the original set. So just upon visual inspection, that seems to be heading us in the right direction. Okay, going to quit out of there. Stat calc, lin reg. I want to do a linear regression equation with L1, L3, and we'll store it directly in Y1. And calculate. Take a peek to make sure it's in Y1. It appears to be. Let's hit graph. Appears to fit that data pretty well. Put that equation back again. And that would be the generic, but it's actually the square root of y. And x. All right, if we're going to use the generic xy, you want to make sure that you are defining what these things are. So y represents predicted cost. X represents width in feet. And if you want, you can incorporate those into the variables themselves. We've done that a bunch of times. Right, why do you think your linear model is appropriate? Well, the two things we can go to, not the only two things, but two things that are readily available, is the scatter plot of the transformed data appears to be linear. And then we will go to the residual plot. So let's turn that first one off. Turn the second one on. And L1 resid looks like it's all set up. Turn off that equation. And let's zoom 9 it. And I think I may have forgotten to turn that plot on. Yes, I did. Zoom 9 it. And I would say that that looks like a pretty randomly scattered pattern here. So in terms of other things we've talked about, we can incorporate the correlation, incorporate the coefficient determination. You could do a significance test on the transformed data. You could build a confidence interval. There are many, many ways we talked about to justify this. Those would be the two cleanest, fastest ways of addressing it in that small amount of space. Okay, find the predicted cost of a square deck that is 10.5 feet wide. So they're giving us a width and asking us for a price, or they're giving us an X and asking us for a Y. So if we type the right-hand side of that into our home screen here, negative 0.135 plus 3.174 times 10.5, that gives us the square root of y. So to get that y by itself, you have to square both sides. So we can just take that answer and square it. And depending on what the rounding instructions are, we're just going to go, it's about 1,100 bucks. All right, one issue that's inherent to this little corner of the math world, I did this calculation based on the 3 decimal places. If we did that calculation based on that equation before we did any rounding, the answer would be a little bit different. If you're going to show this work, then that answer needs to match that work. If you're going to be doing it working off all the decimal places in the calculator, then it's going to be a little bit different answer, and you have to indicate that. This is more of the preferred, probably what they're going to want to see on the AP exam. Okay, last part of this. Is it reasonable to use this model to predict the cost of a square deck that is 20 feet wide and explain? Well, our X values only go from 4 to 15. That's a pretty decent extrapolation beyond what we have here. If we're going to go to like 16 or 17, maybe all the way up to 20, I'm not a civil engineer nor a construction guy, but there might be a whole new set of issues once you start getting a deck of that size that would affect the cost. So I would answer this as 20 feet is an extrapolation. It may not be reasonable. Now, you don't want to say, unless you are a structural engineer or a construction worker of some kind where you have first-hand knowledge of the extrapolating the 20 is definitely going to affect the price, it may not be reasonable. It may not be a safe recommendation, extrapolation. You don't know. You're not an expert in this field, but in a statistical sense, this model may not be valid. The next problem we're going to go to is number 2 in the same packet. It says, during a chemistry lab, students were asked to study a radioactive element which decays over time. The results are in the table. And it gives us the data, and they're giving us a specific transformation they want us to use. Now, yesterday when we did the transformations, we used natural log. There's no law that says it has to be natural log. It can be log-based, anything you want. Typically, if you're going to be introducing logs, it would be base 10 or base E. In this case, for this problem, we decided base 10 rather, was a little bit more appropriate. So, I think I have this already set up in a calculator. Yes, I do. What we're going to do is take a quick peek at the scatter plot, get a feel for what we're dealing with here. And we get data that it definitely appears to have a curve to it. So using the transformation they're telling us to use, what I'm going to do is in L3, put the log of all the y's, or log of everything in L2. So log of L2, enter, and now when I do my regression, I'm going to use L1, L3. Quit, stat, calc, and then reg, L1, L3. We will store this in alpha F4 and hit calculate. And it doesn't look like I turned my diagnostics on. It's okay. We really don't need them for what we're doing right now. So if we go 3 decimal places, we have y hat equal to, at log y equal to 2.505 minus 0.075x. And as a reminder, if you're going to be using the generic xy, you should be doing that x y hat equals thing. For the interest of time in this video, I'm not going to go through it for this problem, but that should be there for full credit purposes in a free response environment. All right, let's take a look. The y equals appears to have that equation in there. I am going to adjust that scatter plot to show L1, L3, and we'll zoom 9 it. And it appears as though that transformation linearized the data. It appears as though that equation fits the data pretty well. If we really wanted to be super sure, so to speak, we would take a look at the residual plots. We're not going to go there in the interest of time. We just did that in a previous example, but for more convincing evidence, we would want to do that. All right, as far as the prediction goes, they got very tricky on us here. This is time in days, and they're asking us for the predicted amount of the element after 30 minutes. So we have to convert minutes into days in order to do this. Well, 30 minutes is a half an hour for 0.5 out of 24 hours. Now, the calculator doesn't care whether this is in reduced form or not. If you want to reduce it to type it in, you can. We got log of y is equal to 2.505 minus 0.075 times 0.5 rather out of 24. So when we type this right-hand side in, it's going to be log of y equal to that. Remember, log without the subscript is understood to be base 10. So it's equal to that number we get. So it's going to be 10 raised to that power gives us the y. So we have 2.505 minus 0.075 times 25 divided by 24, and we get that answer. And then 10 raised to that exponent, and we're going to get a final answer of about 318.719 grams. And we'll do a quick check. Does that seem to make sense? Well, 30 minutes is pretty much right after the whole experiment began, so there's not a whole lot of time for this element to decay. So we expect something pretty close to 320, just a hair less. And we got it, and we're good. Also, as a reminder again, if you did these calculations with the multiple or the more decimal places within your calculator, your answer would most likely be a little bit different than this. But if you're going to show this work, that answer needs to match this. And that's probably what they're going to be looking for as far as the rubrics go that address this skill. All right, let's take a look at the front page here. And here we're already given an equation, and they're asking us to make a prediction. So let's do some stuff here that's a little bit different than what we've seen. So the one that's kind of catching my eye right here would be number 3. So the explanatory variable is the length of the rat in meters. The response variable is the weight of the rat in grams. And this is our equation we're working off of. So we're plugging that 0.13 in here. So we got the cube root of the y value is equal to 3.69 plus 3.012 times 0.13. So we type that in our calculator. That's equal to the cube root of y, and then we'll cube that result. Now, although the final answer is a round off, when it comes to things like this, we prefer not to have too many more round offs. I'm a big fan of just typing it in the calculator all in one shot, if at all possible, without doing an intermediate rounding. That, and we're going to raise that to the 3rd power, and we're looking at about 68, and our unit here for the y variable is grams. So the predicted weight of a rat that is 0.13 meters long is about 68 grams. All right, let's take a look at this one here. This has got 2 logs in it. So our explanatory variable, shooter's distance from the target, response variable, the distance from the bullseye, and this is our equation. So we want to predict what happens when that distance is 50 meters. So what happens here is we have log base 10 of y, if there's no subscript that's understood to be 10, equal to 0.72 plus 0.61 times the log of 50. So all of that can be typed in the calculator, and that represents log base 10 of y. To get at y, we raise 10 to that power. So 0.72 plus 0.61 log of 50. And then we're going to raise 10 to that power. And we get about 57 millimeters. Or in other words, the predicted distance from the bullseye is about 57 millimeters when the distance from the target is 50 meters. So that puts it in context using the appropriate verbiage. So we did an example of the square root transformation with the deck problem that we finished a few moments ago. We did an example with just one log with the chemistry problem we did a few moments ago. Mixed in a cube root, mixed in 2 logs that were not base E one we did yesterday. So I think that that's a pretty good sampling of of the skills from what you need from these worksheets. Let me just take a quick look and see if anything else is jumping out at me. I would say if you're going to be trying one on your own, this would be a good next one in terms of similarity to what you would need to know for the upcoming quiz. The ones with the years, not that they're bad problems, they're a little bit more time consuming, and it's a little bit more than what you're going to have to do for the next quiz.
I think that is a wrap.